Ogilvie from Australian National University.
Good afternoon, everyone. There's only a few more trees to go today. So I'm going to be introducing a new version of StarBEAST called StarBEAST2 that I've been developing with my PhD advisor, Alexi. We all know that gene trees often differ from... Okay. We all know that gene trees often differ from species trees. And there are a number of processes that can cause this discordance. There's gene duplication and loss, which can cause paralogs to be inappropriately treated as orthologs. There's introgression and hybridization. There's horizontal gene transfer, and there's coalescent processes, including incomplete lineage sorting. My focus is coalescent processes because in multicellular, sexually reproducing eukaryotes, while the other processes can occur, coalescent processes always occur. There's a number of types of error that are caused by these coalescent processes. Very famously, there's the anomaly zone that causes topological error, where if you have an asymmetric species tree, when the internal branches are short enough in coalescent units, then one of these symmetric gene trees, or all of the symmetric gene trees, will be more common than the asymmetric gene tree that corresponds to the species tree. And this causes maximum likelihood concatenation to be statistically inconsistent. Another important type of error is divergence times or branch lengths, where looking backwards in time, if two species have diverged at time t1, we don't expect all the alleles to coalesce at that time. Instead, all of those alleles will coalesce at a more distant times with the expectation of t1 plus 2ne. Multi-species coalescent models incorporate the coalescence, so they should be robust to these errors. There's a couple of types of multi-species coalescent models. There's fully Bayesian methods, which take advantage of Bayesian's rule to characterize the posterior distribution of species trees given a set of multiple species alignments, multiple sequence alignments as your data. They do this using the phylogenetic likelihood, which is the likelihood of your multiple sequence alignments given your gene trees, the coalescent probabilities of your gene trees given species trees, and the prior probability of the species tree. In contrast, maximum likelihood summary methods return the single most likely species tree, which is determined as being the tree that maximizes the likelihood of your gene trees. So StarBEAST is a fully Bayesian method. So it uses MCMC, Markov chain Monte Carlo, to jointly estimate the gene trees and the species tree. Now, the Markov chain Monte Carlo needs to explore your probability space, and it does this using proposals. This is an example of a very simple probability space. It's just a two-dimensional mixture of Gaussians. And you can see here that the MCMC explores the space using proposals that change the x and y coordinates at each step. And the same applies to more complex spaces. It just takes many more parameters, and the space is more lumpy usually. So as next-generation sequencing has appeared, people have been collecting more and more and more and more loci to do their phylogenetic inference. And this has highlighted an issue with StarBEAST. And the issue is that as you increase the number of loci in your analysis, StarBEAST scales pretty poorly in performance. You can see here that for every time you double the number of loci, the number of independent samples you're collecting per hour decreases by about 6-fold. And that's regardless of the number of species in your tree or the number of individuals for each species. In response to that, a lot of people have started using summary methods, where the input data is typically gene topology frequencies. These include MPS, Astral, Standard Star, and these methods are very fast, and they're particularly fast when you consider that the gene tree inference step is easily parallelizable. But these methods, they estimate the species tree topology, and if they return any branch lengths, they do so in coalescent units. You can't use them to estimate divergence times or substitution rates. And using a simulation study, we've shown that concatenation maximum likelihood actually does not do a terrible job at inferring topologies, even given shallow phylogenetic inference. Given 4,000 loci, you can see here XML estimating a species tree with a topological error on average of less than 1 Robertson folds unit away from the truth. In contrast, concatenation maximum likelihood does a really bad job at estimating the branch lengths. In our study, we found that StarBEAST using just 4 genes does a better job than concatenation using 4,000 genes. One place in the tree that's particularly severe is in the tips. You can see that the length of the branches of the tips, so the ages of the extant species, are dramatically older when inferred using concatenation compared with inferred using maximum likelihood. Sorry, compared with the multi-species correlation. And just this year, a new concern with concatenation has been reported, which is spills, or substitutions produced by incomplete lineage sorting. So this is the observation that if you have a mutation on a discordant gene tree, if that mutation is in the discordant branch, it has to be explained by multiple mutations on the species tree, which is expected to cause incorrect estimates of substitution rates. So, to try and resolve this, we've developed StarBEAST2, and StarBEAST2 improves the computational performance through a combination of analytical integration of population sizes and new coordinated MCMC proposals. It also, for the first time, estimates per species substitution rates in a multi-species coalescent framework, and it's available now in BEAST 2.4 and above. So first of all, StarBEAST always estimated population sizes using MCMC. So that's done by estimating the probability of the gene trees given the species tree and a vector of population sizes theta, and having a prior distribution on those population sizes. Here, in this example, a lot but the operators, the proposals that we've added to StarBEAST2, they're a new set of proposals and they're more powerful than what's in Stacy's. When you combine analytical population size and these coordinated height changing proposals, you get a 4-fold increase in performance. So that's what we're using as the default settings in StarBEAST2. Interestingly, analytical population size only seems to help when you also have the height changing operators. And the adding the topology changing operators seems to slightly decrease the performance in terms of the number of independent samples drawn per hour. StarBEAST2 also introduces a multi-species coalescent relaxed clock. So this clock model, under this clock model, the rate of each gene tree branch is the weighted average of the species tree branches it traverses. So in this example, you can see that gene tree branch little a spends 2/3 of its time in species tree branch A and 1/3 of its time in species tree branch AB. So its rate will be the average of those two rates, but with big A assigned a weight of 2/3 and AB assigned a weight of 1/3. In a simulation study, we can see that StarBEAST2 more accurately infers first BC rates than concatenation does. And in fact, when you increase the number of loci in concatenation, it's actually increasing the error in your inference. This is just plotting the rates that we simulated against the rates that we estimated using StarBEAST2 and using concatenation. And you can see that StarBEAST2, the estimated StarBEAST2 and concatenation rates cluster around 1. That's because 1 is the expectation of our prior distribution. When we increase the number of loci by 10-fold for concatenation, you can see that the rates are really only dispersed, that you have a lot of very high and very low rates that are unrelated to the true rates, and that's probably caused by this spills phenomenon. So, from our simulation studies, it looks like concatenation is relatively okay for species tree topology in the sense that it does a much worse job at estimating branch lengths or substitution rates than it does topology. So my suggestion is a shift in focus away from summary methods that only estimate topology to methods that can estimate branch lengths and substitution rates under the multi-species coalescent. And I think something that's kind of cool is that something that would take StarBEAST 1 month is only going to take StarBEAST2 1 week. I'd like to thank all of my PhD advisors, Alexa Drummond, Craig Ritz, and Jason Bragg. I'd also like to thank Tim Vaughan, Joseph Hellett, and Remco for their help and insights into BEAST2 and the multi-species coalescent. And I've got my photo credits there. And thanks everyone for coming.